Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video we are going to mention how to check for punching shear in flat plates and how to fix any problems in those punching shears via using a crown plate or basically a drop. Some people call it crown for column. Now, it doesn't matter really what it's called. What I'm trying to say is that you might increase the thickness of your slab in this position, or just make a crown for the reinforced concrete column. So we're gonna basically talk about those two things very quickly, and I hope you enjoy this video. So alright, first of all, I want to give a whopping shout out to all my dear subscribers, especially Engineer Donald Khanye, for providing some insights about some points I might have missed, as well as some basically very fruitful questions that I will address either in this video or in the next upcoming videos. So once again, a huge thanks to all dear subscribers. I do actually read all of your comments. Even the comments on old videos are read by me and are replied to. Now, with that being said, let's jump into Autodesk Robot and take a look what we're going to do today. Now, today I'm going to once again model a simple slab, and this time I'm going to just make me like, I don't know, like 3 spans. Each span is 5 meters in the X, and maybe 3 spans. Each span is 4 meter in Y. In the Z, I'll leave it, I'll apply and close. Now, please notice that I'm assuming that you do know those basics in Robot. If you do not know the basics in Robot, then please double check the basics video series that I will link above. Anyway, I'm just gonna go to Slab. This time I will avoid all the mistakes I hope that I made in the last video. So I'll just do it in first time correctly. So I'm gonna take slab thickness 200, checking. It's constant 200 with reduction of moment of inertia of 0.25 according to the ACI code. So I'll go to rectangle, click my 3 corners, and of course remember that my first line is the x-axis so that I can read the results later. Now for the columns, I'm gonna go to column and I'm gonna select me. Now this is only one story, so I don't think some large columns are needed. So I'll go to reinforced concrete column, select RC 300 by 300, which is a 300 by 300 column, and I'll start clicking now. If I click on a corner, it will actually create the column and push it all the way down. So by the power of video editing, those columns were added. A nice touch I want to show you here is that the Autodesk Robot actually draws you the column outline. Now this column seems to be odd because it's not really carrying the entire plate, and that is unfortunately true, but this is a limitation in the finite element method, as you know that the edge point must connect to the center of the column, although in reality it's actually a little bit inside. Now you could, hypothetically, you could just draw the column here, for example. Let me show you. You could draw the column here, which would satisfy the beauty of having a column inside the slab. However, in reality, if you do this, then the rest of the slab is considered cantilever outside, so it will be developing negative moments, which is not really the case. But well, I mean, those are inaccuracies we have to deal with using the finite element method, and that's the reason why factors of safety do exist. So I'll quickly delete this because this column is not what I wanted. So I delete my column, the one that I added just for aesthetic reasons. I have my columns, I have my everything. I'm just gonna go quickly add me dead loads and live loads. Remember, once again, my goal here is not to calculate dead loads and live loads in detail. This is something you would have learned in the basics courses if you are still a civil engineering student. Of course, if you are a professional, then I mean, we all know how to calculate those loads. For me now, I will just assume me once again a 10 kilonewton force going downward in the dead load and a 3.5 or 4, I don't know, kilonewton force going downwards in the live load. And I'm gonna quickly go to loads, manual combination, make me an ULS combination. I say here ULS for this as a name, and add those two factors. I'll apply that, and before I close, I'm gonna take me a new one, select SLS, and select, well, SLS. I just write the name SLS. And I'll select my dead load, go there, and select my live load, go there, apply it, close, and now I have my combinations. This is a quick rundown of what we've done last time, with difference being that now I have columns instead of points. If I run the analysis now, nothing should phase us. It says separate structure. Well, that phases me. Okay, I think I messed up something, so well, I'm not going to video edit this. Let's take a look how I can know where my instabilities are. There is instability of type 2 detected at node 2 in radius in direction RZ. I want to continue, so there is a lot of instabilities. Let's take a look why. Okay, so he said node 2, right? So let's take a look on node 2. Node 2, node 2. Where is node 2? This is node 2? No, this is node 3. That's node 2. Okay, and why are you unstable? So something strange that kind of raises the red flags here is that the slab was not discretized, so I'm pretty sure I might have messed up some of my definitions here. Let me just check. Let's click on the slab, check out how it was discretized. So calculation model, curtain wall. No, I want the shell, and I wanted to discretize the shell. So I guess now it will work. So let's run the analysis again. I don't have any separate structures. Yes, now it's discretizing. Everything seems to be fine. So, a little thing that you miss here might just cause cascading problems everywhere else. Anyway, I have my analysis ready. I got just to maps to quickly check if everything seems to be okay-ish. So let's take a look. Maps MX as I'm expecting, and maps MY is also as I am expecting. So far, so good. Now, with that being said, I can well design this, but spoiler alert this time. This time the punching shear is going to be checked, and I don't think it will work. So let's take a look at this, because my slab is very small and I have 5-meter spans, so I don't think it will work. Anyway, let's check out two things. First of all, if you show the deflection very quickly on maps and just click on UW, you notice some severe deflections of 15 millimeters. This is too much for me, in my humble opinion, like 1 centimeter. I mean, this is basically a lot, to be honest. So I don't think this slab would pass any code checks for deflection. Now, of course, I try to keep this video as code neutral as possible. This is even not correct because we are now on dead load. If you go to SLS, you have even larger deflections, 19 millimeters. Now, there are some codes, depending on the code. Some codes check out the live load deflection alone. Some codes have limitations for dead load alone, live load alone, and the combination of both. It depends on your code, but please take a look on this. Of course, if your deflection is too much, then you have to increase the thickness of your slab or think of beaming it, making beams there. Notice that my distances are 5 meters, I think, and in X, and 4 meters in Y. So it's pretty big, and 20 millimeters or 200 millimeters might not be enough. But I leave the decision to you. You have your own codes that could help you. What our dear subscriber Donald Khanye mentioned is that there was a question that I will address later about what this U is. Now, in this case, in our view here in maps, the Z here is the short-term elastic deflection, calculated, of course, using the reduced inertia, the 0.25 I gross. Please notice that the long-term deflection is even larger than this, because concrete has long-term deflection calculations that sometimes could be twice or whatever is that you get in the short term. So, of course, once again, you have to refer to your codes to check how to calculate long-term deflections and what kind of limits you have to compare with those. But for me, usually seeing the short-term deflection of this would be and comparing it on my code limits would give me a very clear indication that things are not really going as smooth as I want them to be. But well, to address this issue, you could increase the thickness. Allow me to show you that very quickly. If you increase thickness to, I don't know, thickness 300, for example, and add and close that, let me show you the difference very quickly. If you change the thickness right now and run the analysis, now I changed the thickness to 1.5, so I think it should be 1.5 cubic, the effect. So it's like, I don't know, like 3 times less. So 19 divided by 3. Yeah, because, I mean, how do I know this? And here is a nice piece of trivia for you. Let me show you how I could very quickly understand how much deflection I would get. Anyway, the point here is that for the 200, the max scale was 19 millimeters. Now, I want, for example, let's say that I am targeting short-term deflection of 10 millimeters. If you have a certain deflection and you want to reduce it, you put a target deflection in your head, let's say 10 millimeters, for example, and then you see the ratio between the two deflections. Like, let me explain very quickly what happened. Deflection 1 was 19 millimeters around, or 19.5. Now my target is, let's say I put a target in my head, it's 10 millimeters. So the ratio is, well, basically 1.9, which means I need to increase the inertia to 1.9 times. So the ratios are 1.9. What I'm trying to say is that, well, the 1 over EI before and the 1 over EI after, there is a ratio of 1.9 between them, because if this 1 over EI old gives you 90 millimeters, then you want the 1 over EI new to give you 10 millimeters. which means that if this is 1, this needs to be at least 1.9 times 1. Now, it's not really accurate, it's just a very quick approximation. Of course, you need to inverse and find a longer calculation for that. What I'm trying to say is that I found that I need to increase I to 1.9. This is extremely approximate. And you could actually derive more equations based on that. This is only food for thought for you. Anyway, well, I want to increase EI by 1.9 fold. Now, E is impossible to be touched because concrete, but I is possible to be touched. So I want I new to equals 1.9 I old. Now, we know all that I is actually like a cubically proportional to your H. So if you want 1.9 times, you would have to increase your H by what? So you need to take the third root of 1.9, which means you're going to take the cubic root of 1.9 or raise it to the power 0.33. Now when I did this, it gave me 1.25 or something as a result. So what I did is I took the thickness of 200, multiplied it by 1.25, I got thickness 250. And that's how I was able to successfully predict what thickness I need to find the deflection that is required. Of course, this is once again a disclaimer here. This is a very quick rudimentary idea to predict thicknesses, but of course, in the end, it's your responsibility to keep trying until you reach a thickness that you feel is okay. Now, I will put it back to thickness 200 because I think I wanted to fail in punching, so put it back to 200. Now, we are back to our thicknesses of 200. I run the analysis very quickly again. And now I'll go to design. First of all, I'll select my slab like this, go to design, go to provided reinforcement of RC elements. And this will lead the robot to basically import the slab into the designer. Now, because my slab has not yet been designed, it will basically tell me that it's gonna design the panel. So, okay, be my guest, it's gonna design the panel. Now, see, transfer of RC elements has been completed. Thank you very much. If you go to story, go to slab, you see the slab there. As far as I'm concerned, I think he's still using the reinforced concrete floor as my design model. I need to check that before I continue any further. So let's take a look on this. We go to required reinforcement just to make sure everything is fine. And let's see, he is using what kind of reinforcement type? RC shell. Let me just quickly check by going to structures, geometry. I'll select my thing here again, double check. It's using an RC model of RC floor. Okay, so remember that RC floor is basically the model where only bending is being designed. The axial forces are not designed. Also, this is okay for now because the axial forces in the slab are actually negligible. You can ignore them. We go back to our provided reinforcement for slabs. I hope it still sees it. It does. Now, one cool thing that one of my dear subscribers, Donald Khanye, mentioned is he mentioned that I forgot something. And he's right, by the way, because I explained wooden armor theory of bending design before. He rightfully mentioned that you are designing for ULS and SLS and using the limit states, but however, you forgot to change this to wooden armor. Now, the wooden armor method was a method I explained before in a video linked above, the previous video of the slabs. And it's kind of a way of incorporating the torsional moments, moment xy and moment yx, which are basically the same equally, to incorporate them in your x strip and y strip. Now, this is a technique that is used by other softwares like eTabs and Bluebell FM and so on. So if you want, you can. Of course, if you use analytical, then it just uses the x and y. With an armor, will calculate the torsional moments in the reinforcement. So if you click on calculate now, you get this basically. Now, you see now he says that admissible deflection value has been exceeded for panel number 1. Okay, thank you very much. Now, panel number 1, where is it? Well, it's only one panel actually, but it says that the deflection has been exceeded. And by the deflection here, I think he means the long-term deflection. Allow me to show you. So what was our deflection? Now, our deflection based on the results, the analytical results, like they were not really near any permissible values. You get 15.5. I need to select the correct combination. So I'll just quickly go to structure model, go to geometry, and select me the SLS case. So let me just go to SLS. So 19 it is. If you go to slab, provide required reinforcement, just to make sure everything is fine, and then calculate, it says, well, deflection is too much. Now, why is that? Well, allow me to show you. So, if you go to SLS here, you go to deflection, there is deflection U. Let me show you what this is. If you click apply, you get 34 millimeters. Now you have two deflections. There is deflection U, basically the Z deflection, and you have deflection U. I think what is meant by this is deflection upwards, but I don't think there is any deflection upwards, and that's why you don't get any deflection here. You get zeros. So deflection U is deflection downwards, as far as I know, because it's also on the negative side. Notice, and this is once again another good hint our dear subscriber that Khanye has mentioned, the deflection is 34 millimeters. So what gives? Well, I think I have a good answer for this. What you see here for 34 millimeters is the long-term deflection. Because if you go back to geometry, you will see that the short-term deflection, the SLS, now I need to delete this because he's giving me the long-term deflection. So let me remove everything. Go to Results, Maps, to U in SLS, and I click Apply, and you get 19.19. So this 34 millimeter is some kind of odd. What gives? Why is it 34 millimeters? Well, the answer to that is that this is the long-term deflection. Now, I said before that the long-term deflection is between 2 times to 2.5 times the elastic deflection. So let's take a look if that's the case or not. Now, let's calculate again, just in case something is missed. It still warns you. And if you click on deflection U and click apply, you see 34. Now, 34 to 19 is around, I don't know, around maybe 180%. It's less than 2, but it's still like the approximation of 2 to 2.5 still stands. There is more stiffness factor and stuff like that. I will talk about this later. For now, no. So what I'm saying is for stiffness factor, I will talk about this later. It warrants a deeper dive, to be honest, because what exactly the meaning here is and how this is used will be subject of another video. But for now, I'll talk about deflection. Deflection down 34 millimeters. It warns you because you have asked it to warn you. Now, where did you ask it to warn you? If you look here, you don't see anything. There is no warning system here. So where was the warning issued, and where exactly is it that you ask it to warn you? Well, it's here in the slab shell reinforcement model. It is an RC floor, so if I double click on that and go to SLS parameters, you see that you are asking it to warn you if the deflection exceeds 30 millimeters. And that's the reason why. Now, of course, allow me to show you something really good. This is for 60 months, by the way. And ratio of loads long-term to variable, we're assuming it to be 1. I will leave it. This has a meaning in code. But allow me to show you what happens if we make 3 months, like just after. Now, if we make 3 months, it's going to be strange, but I think even the deflection will be close to 1, if not less. So let me show you what happens. Oh wait, I cannot change this, right? So I need to go to my own core reinforcement, go to reinforcement parameters here, and I'm gonna change this to 3, and we'll add save and close that, and I will use it here and apply that and run the analysis yet again. So let's take a look. Now I am after 3 months. It was 19 point something, but now it's 26 point something. So you see, it's not as much as after 60 months. So what I'm trying to say is that, well, it depends on what's the time of calculating the long-term deflections. Well, in this case, it's 33 millimeters, and Robot is warning you that this is too much. Now, first of all, Robot calculates the long-term deflections for you, but I just want to remind you that, hey, you are responsible of checking your code requirements and checking what is exactly measured when. Because I think, of course, it depends on the codes, but I think in some codes you have limitations for deflections after immediate loading, the short-term deflections, and you would have limitations for live load and limitations for dead load separately. You might also have a limitation for both of them for the long-term deflections. It depends on the code, and you have to basically check this out. Now, that's not why we are here. We are here to check out, well, punching shear. So how can you check punching shear? Well, if you go to slabs punching, you are greeted with this, but the punching shear has not yet been calculated because, well, it cannot calculate punching shear because you don't even have the steel designed. I mean, the only thing you have here is the required area steel, but you do not have the steel bars designed and applied, and so the punching shear is unable to be calculated. Well, there is a reason in the ASI code I can mention, and maybe it's even in all codes. It's because the punching shear requires, in ASI code at least, for you to know the D, the distance between the tension steel and the top concrete, basically. It's called D distance in ASI codes. So you have not yet designed your steel, so well, you cannot even check punching shear. Now you could check punching shear directly, but no, I want to first of all get the provided steel. Now I've explained this before. I will just run the analysis now. I think it will do you wire meshes, and suddenly, boom, you got this problem where everything is bad in punching shear. So I mean, if you look, seems the structure gets designed. Of course, he's using wire fabrics here, and you even get, and this is a little bit misleading, and you need to get warned about this. If you go to slab reinforcements, you will see the wire fabrics being done, but you see it's incorrect. Whatever you do now, this is not enough because your punching shear has failed. You will see this by seeing the question mark here, but that's not all. If you click on calculation node, I think you should see the punching shear failing. Yeah, there we go, in red. So don't get like this little illusion where you think everything is fine. And there is something strange in Robot. If you click on drawings, it will actually show you drawings. And this is kind of worrying for me because if you see drawings, you would assume that, well, everything is fine. Now, this is worrying for me because no, not everything is fine. Actually, everything is not fine because the punching shear has failed. So please be aware that, hey, you should, even when you see punching shear in red, you should be really, really worried. Also, before you export anything, just double check your calculation node to see if you have any red lines, which are here, which means that you should not even rely on the design here. So we need to go to punching shear and fix that. Now, if you go to punching shear, you will be greeted by this screen where you have multiple red lines and multiple green lines. Now, what are those lines? Those lines are the punching perimeters. You know from various codes that if you have a column, then you move a distance away from the column to get the punching perimeter. This is code related, and I will leave it to you to know exactly what this is. But of course, the internal columns were safe because the punching perimeter is large, which means that the punching resistance was large. However, the edge and corner columns are not safe. Now, in various codes, you should notice that there is a difference in various codes and their design equations about what an internal column is and what an edge column is. You can actually see this in action here. For example, if you click S1, this is like support number 1, which is this one, as you can see. You see that, well, it's an edge column, and it's, well, if you look here, S1, this is 5En resistance, this is VU, and this is the shear perimeter, and that's your shear factor, which is really abysmally low. Same thing applies for the other ones. I mean, the only ones that will be green are the internal columns, yeah? And it's kind of like disheartening to see this. Now, you could try fix that by immediately assigning a column head. This is not a drop panel here. This is a difference here. A drop panel, now, theoretically speaking, they are both the same in terms of punching shear, but I rather would say that drop panels are panel related, whereas column heads are column related, as the name suggests. So you could try, allow me to show you. You could go to S1, click on it, click select it from here, and you could even group them. For example, you could group all the columns that are on the edges together, and the corners, sorry, together, and on the edges together, and deal with those two groups separately. But I will deal with them one by one. If you click S1 to show you, you could create a column head. It could be, now, if you click create column head, it actually creates a column head around the column, and you can see it here. If you click on front, for example, or if you click on 3D, you can see the column head being generated. Don't be disheartened by the weird off center that you see of the column. I explained the reason behind it. Now, the column head was not really good enough to make it work. You could change that by changing the length and distances of the column head, which would change the factors of safety until you get a safe column. And you can see that it's green now, so everything is to be fine. Now, of course, you could do this one by one. I will just show you, for example, for S2, which is an edge column. Now, an edge column, I don't think it will need a big column head, but, well, for practical reasons, if you make a column head in a certain size, you should do the same column heads everywhere because of aesthetics, basically. Now this is one way of solving punching shear. And this is, well, basically what ends this little video nugget I wanted to talk about, because I want to talk about punching shear. Now, the second part of this little video nugget is about slabs with drops. Now, how can I make drops? Now, as easy as it sounds, it's actually really easy. Now, to do that, well, first of all, if you decide on making drops, then this means that you are basically doomed. Like, you should have done this in the beginning. What I'm saying is, you're basically gonna, if you, after all this work, decide to do drops, then you will have to rework most of what you've done before. It means that your entire slab system is to be scrapped and you have to start all over again because drops need to be drawn again. So I just go to design, go to provided reinforcement and delete this slab because it never existed before, so my slab is deleted. I go to structure model, to geometry, and delete my slab because this now, ladies and gentlemen, is unfortunately a waste of time. So I'm gonna make me a slab with drops. Yes. So we're back to ground zero where I have those columns. Now I will make me drops for most columns, if not all. So let's do that. And well, how do I do that? Well, I'll go to plan. Now I want to make me drops. So let's say that my drops are, this is something you need to know yourself. Let's say my drops are at 700 millimeters width and length and are at, I don't know, like 500 maybe or something thickness. This is something you decide. Depends on your architecture. So okay, I want 700 millimeters width and height, so it's actually 0.35 because half of it. I'm gonna repeat it 3 times at distances of 5 meters. That's a little trick, I know. So now it's gonna make me 0.35 and always jump 5. So this should work. And if I hit apply, you get the first part of the drops. Now I go to negative 0.35, the other half of the drop, and I'll add that. And now I have my starting and finishing of the drops. I go now to Y, same thing applies, 0.35 is my starting point of the drop. I want it 3 times, I guess, with a distance of 4 meters. I'll add that, which means we'll add 4, 4.35, and so on. I'll apply that to check. Yes, seems legit. And now I'll go here to negative 0.35. I'll add that, and now I have my grid for drop panels. There is one mistake you could do. Now, do not, under any circumstance, do not just draw one big slab and then draw the drop panels above the slab. This is not how finite element works. Like if you draw, like imagine I draw one big slab like this because I'm so lazy, and then I draw a drop panel above it. That's not how finite element works. Because if you draw another panel like this, then what ends up happening is the stiffness gets added. Now, if you make a panel of 500 and draw it on top of a panel of 200, this means that the stiffnesses get added and you have a panel of 700. You would think, well, that's easy. I can make me a difference. Like, okay, if I want to have 500 drop, I have 200 millimeter thickness. Like you would think that, and this is incorrect, by the way, you would think that you have 200 millimeter thickness and you want a drop of 500 millimeters. So all you have to do is to add 300 millimeters on the slab. I don't think this will work because in punching shear, then the robot will get confused as to which thickness to use. So it's kind of annoying. Now, please, I am saying this based on my knowledge in finite element methods. But of course, if robot has a magical solution to that and it seems it's working, then please, well, feel free to tell me in the comment section. Now I'm gonna go here and define me a thickness of 500 here, 500 millimeters. Reduction of moment of inertia, I'll just keep it, no problem. I'll add that, close, and start drawing. Now, once again, you could draw from the edge, but I've explained why this is actually weird and you should draw like this. So I have this. Now, this is going to be a nightmare of drawing, by the way. You will soon realize how not easy it is. Anyway, I'll video edit this, so stay tuned for video editing. Just want to let you note that while I was drawing the shells, I was making sure that the first line is horizontal so that all of them have the same x-axis orientation so that the reading of the results makes more sense and that all of the plates show you the exact same x-axis, not that you get x and y together when you ask for local directions. So yeah, back to video editing, I guess. So yeah, that's now a plate with drop panels. Now the drop panels are 700 by 700. You can make it larger, you can make it smaller. This is of course your decision as a designer. I just put 700 by 700. Now off we go to loads. I hope that the loads were not deleted. I hope that, I really hope. Oh, there they are. Amazing. So if I say all here and I say all here, with this little trick, I think everything should be loaded, right? Let's show. Beautiful. Okay. So I think we've done that, right? I think we're done. Run the analysis. I mean, you know the drill, right? Run the analysis. Double check very quickly. Never underestimate the power of double checking. Now, the next video is going to be about finite element mesh generation. So I'll be tackling this stuff and talking about this. For now, I will just continue using this dumb mesher, and I will be talking about finite element mesh generation in the next video. So I'll just continue now, ignoring the abomination of a mesh because I want to have a separate video for that. So okay, never ever trust anything you do unless you double check the sense of the results. So well, deflection shape, well, that checks out, seems to be okay. Going to results, diagrams for members, no, I mean maps, mx, just to see if the stripes work, and they do work fine. My, everything seems to be fine. Deflection u should be okay, perfect. 3.8 millimeters? Why? SLS, yeah, 20. Okay, fine. Now it makes sense. Once again, I want to reiterate the importance that the engineer checks his deflections and, well, double checks with the code authorities. So now I go to analysis. I think I didn't choose the correct thickness. That's a bummer. Well, you can see at least the errors you will notice, and you can, well, fix the errors. So let's go back again to very quickly check. I will go immediately to provided reinforcement because everything I want to explain has been explained. I go to design, provided reinforcement immediately. Notice if you go to provided reinforcement immediately, it will calculate very quickly based on the basically givens. Okay, let's take a look on what we have. Did it work? Okay, let's run the calculations for steel. I don't think it will work because it will not understand it's one slab. Yeah, see, it cannot understand this because it cannot obtain provider reinforcement in the appropriate area, and he's talking about this. I'll explain how you could find practical solution to this. Now going to shear design again, most of them are not working because it was unable to design, I guess. So why is that? It's unable to provide area, and it's unable to basically reinforce the entire thing. Here it's unable to put any steel bars, I guess. Or does it? We can know this from the punching shear. If you go to punching shear, if it calculates something, then it is able to put bars. If it doesn't, then it's unable. Well, look, it doesn't calculate anything, so it's unable. Now, how can I fix that? Now, robot faces a problem in the analysis and design of those drop panels because they are too small. Like 700 by 700 is not a valid drop panel. So you could increase the drop panel to make it work. Option number 2 is actually an easier and more practical option that I will suggest right now because of the limitations of the software. And I'm not making this up. This is what I would really do. I would just basically go back to my single slab approach, thickness 200, shell. So back to the point now, I'll just quickly video edit everything so that we can get back to our original point. So I run the analysis. Now, if you go to, I'll just go quickly to provided immediately. Now, this is one full slab, so robot will not have a problem in understanding how it will provide reinforcement to this thing. So if you go to design and go to provided reinforcement RC, it will immediately import the element, hopefully. And now I have the element. This is to be deleted. This is my old element. If you double click on that, it will run the analysis, and it can perfectly provide reinforcement. Now, if you run the analysis here, you will have problems in punching shear, as we were talking about before. Now, what I suggest as a practical way of having both robot's power as well as your human intuition is, well, you see if you go to punching that those things fail in punching shear. Now, there are two human ways of doing it. Option number 1 is to increase the thickness of the slab, and option number 2 is to use slab drops. Now, we have tried slab drops, as you can see in the video, and due to limitations of robot's ability to understand that the drop is actually together with another slab, it just doesn't understand this, and because of that, it was unable to distribute any reinforcement in the drops, which means it was unable to calculate punching here. So how can we fix that? How can we use the power of robot coupled with human intuition to produce something that is practical and yet accurate? Well, it's actually not really hard. You can go to column head, and well, what was our drop panel? Our drop panel was 700 by 700, I guess. Right? So if you put 700 by 700 and 500, well, this which was this? S3, this fails in shear. You know that your drop panel has failed. So you can increase drop panel to 1000 by 1000, let's say. And now it basically fixed the issue. With your increase in drop panel, it worked. And if you use those dimensions as your drop panel in your design documentation, like instead of having a column head, you could actually use a drop panel in its stead. And that, from my humble opinion, still works and is a practical solution to robots' limitation when it comes to design of slabs when you have multiple slabs besides each other. Now, of course, I will just leave the rest for you. For example, if you want to change everything, let me just make a head here. This is S1. I would use a head of 1000 whatever. I will leave the rest of fixing this issue to you, where you can basically keep doing your column heads until you get everything in the green side. And those column heads are the dimensions of drop panels. There is one nuance that I will keep for you to think about, for food for thought, is that what robot does is it just takes D outside the drop panel, and it never checks punching shear inside the drop panel. So the drop panel's mission in this punching shear check is that it just increases the perimeter of the allowed punching. Now, in reality, if you have a drop panel that is a slab drop panel, then you are permitted to calculate the punching shear inside that drop. Robot doesn't understand this because robot is assuming a column head. This is once again a limitation in the software, but well, I don't think this harms robot much because it has already such amazing and powerful utilities. So I think that a little sidetrack or little, I don't want to say a patch, but the little unhinged thinking of the engineering part would solve the problem. So yeah, I think that is everything I wanted to discuss today. I hope that you enjoyed the video. Of course, there is another video waiting in the pipeline, which is basically about the finite element mesh. It's going to be one singular video for all of those mesh things. So stay tuned for that. Anyway, as per usual, I hope that you enjoyed the video and that it was beneficial for you. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we'll catch you in the next video.